done that. I did not do the car thing though. We have never done that. So you have a one up on me there. So all right. So good morning everybody. I hope you guys are doing well today. It's 9:02, so we're going to go ahead and get started here. 6.01 seemed to go pretty well. Any major questions with our vectors, like resolving the vector or anything like that? The homework assignments, I mean, overall, it went pretty well. No, finding the unit vector. So the unit vector will always give you a magnitude of 1 when you need to find the magnitude. Were some of the answers backwards? That may happen. I haven't checked it out myself to take a look at that, but that definitely well could be. But finding the unit vector is a little bit different than finding the actual vector. So the actual vector is that component form where you're going to do your terminal point minus your initial point. So that's how you actually find the component form of the vector. But then the unit vector, you've got to find the magnitude of that and then multiply through by 1 over the magnitude, because that's going to give you a length of 1 when you have to find the magnitude of that unit vector then. So there's a slight difference between the two. I'll have to take a look at those textbook problems that have the answers backwards. As long as you guys were able to kind of figure out what was going on with that was good. All right, use the resolving vector formula to help you find the vectors if you're given magnitude and direction, because that's when you're going to want to use like the magnitude times cosine of the direction. So you're going to want to use that kind of piece of it, and then you'll want to use like magnitude times sine of the direction to find the component form. So if you're given the actual magnitude and you're given the actual direction, use the resolving the vector formula to help you with that. Yeah, so you're going to have actually cosine and sine as part of your formula. You can, as long as you have a vector to base it off of. So if you have a vector to base it off of and they give you the magnitude of it, you can use that formula, and we did an example like that in the class on Tuesday. You can use it to work backwards to solve for theta, which would be the direction angle then. But you have to have a component vector to base it off of first. So they actually have to tell you this is the vector. Can you find the direction angle for it? So if you have the vector, then you can find the magnitude and you can start substituting pieces into the resolving the vector formula. Arc cosine. It's going to be arc cosine. We did cosine because we focused on mainly the first component of the vector, so kind of that what we would see is in that x part if it were a ordered pair. So we use cosine instead of the arctangent. But yeah, you're thinking along the right lines. All right, any other questions? I see Rebecca's still typing, so I'll hold tight for a little bit here. See what she's saying. Well, she's still oh, I used some of the videos that went with the assignment. Okay, I haven't necessarily watched the videos for a while. I created those over the summer, like, and I was picking and choosing things, so I'd have to go back and take a look. Um, okay, if it was working, that's awesome. I can't off the top of my head remember which ones those were, but I can definitely go back and check because it's been a while since I pulled those. Okay, good. I'm glad that you guys like them. Like I said, I kind of put everything together over the summer time span. So it's been a while since I looked to see which resources I picked and which ones I may need to supplement more with. But I'm glad to hear that you guys are finding them useful. Um, for my juniors out there, I know I talked about the ACTs on Tuesday. You should have gotten an email or maybe snail mail is going out. I can't remember. But yesterday, I think something was sent out by the office as far as ACT locations go. You got an email? Fantastic. So if you didn't get an email, be on the lookout for it. I do believe it was sent out yesterday afternoon ish, maybe. Um, it should have your testing location on where you need to be for the ACT. So again, that's only my juniors. So keep an eye out for that and it will have your testing location. All right, then today we're going to go ahead and we're going to continue with our vectors because remember we are fighting crime with both direction and magnitude, right? Woohoo! All right, so we're going to look at something specifically called the dot product. And the dot product is used for a plethora of things with our vectors. So we'll take a look at a few of those items that we can use the dot product for. You're really going to like the dot product because if we can do addition and multiplication, we can find the dot product because that's all it really is just multiplying and adding things together. All right, so when it talks about the dot product, you do have to have two vectors. So when we're looking at these, we're going to multiply the first components of the vectors together. We'll multiply the second components together, and then we add them. So notice the little dot here, it looks like multiplication. Do not confuse that with multiplying vectors. I'm going to backtrack a little bit because my wording's getting mixed up here. We only know how to multiply using a scalar with your vectors. So when you see this little black dot in the middle, please note that that means to find the dot product. You will always come away with a integer value for your dot product. You will not have a resulting vector once you're done with it. So you should get just one numerical integer value when you're performing the dot product, right? So do not confuse that with just multiplication by itself, which we cannot do with our vectors. We can only multiply by a scalar. All right. Here you can see some other things that we can do with our dot products. So just note that if we're doing it u dot product v, it'll be the same even if we reverse the numbers because addition and multiplication are commutative, right? So if we were to accidentally flip the numbers around, we'll still get the same answer in the end. If you take a dot product or a vector and you want to do the dot product with itself, like u dot product u, that's essentially taking the square of the magnitude. So you can use essentially the magnitude formula and you would square that end result, which basically is just going to cancel out the square root sign from the formula, right? So you'd be looking at the first component squared plus the second component squared. Anytime we're multiplying by 0, we still get 0 as a result, right? So even though we're taking the dot product, you still will get 0 as a result because you are multiplying by 0 along the way. And 0 plus 0 is 0. You can use the distributive property with the dot product there. So if you need to add two scalars first and then perform a dot product, you could technically do the dot product of each scalar or each vector, and then add those results together. It does work like that. And then same thing with scalar multiples. You can take the scalar at the start, or you can wait for to multiply through by the scalar at the end. Okay, so just some properties that will apply with our dot product. All right, let's go ahead and take a look at some examples though. So here are two vectors. Notice the little dot in the middle. We're going to go ahead and use our dot product. So let's start with the first components and multiply those together. So 3 times 5. Yeah, we'll start out with some pretty basic math here this morning to get our brains functioning, right? And then lastly, 4 times 2. Add them together, 15 plus 8. $23. Good. So notice that we do get just one integer value there for the dot product in the end. Your dot product can result in a positive or a negative value, by the way. It doesn't have to always be positive. Go ahead. I'm going to give you a few moments to try part B next. When you have an answer, go ahead, put it on the board or the chat box if you'd like. And hold off on part C because I want to talk about that before we attack it. But definitely go ahead and do part B right now. Looks like we all got -10. Awesome, because -4 plus -6 is a -10. For part C, if you've already ventured forth and tried to do that one, that's great. But that is your linear combination of your vectors. Notice you got the I and the j. So when you want to write that in the component form, you're just pulling the coefficients in front of them. So technically in this 2i minus j, what's the vector in component form that we're technically looking at here? 2, -1, right? You're just pulling the coefficients in front. And then what is the vector of that second linear combination? 3, -5. Yep, or heart -5. If we're going to use our emoticons there. Exactly. All right, so don't make those linear combinations into something more difficult than they need to be. You're just technically looking at the coefficients in front of them. All right, go ahead, venture forth, find that dot product, and throw it on the board. We're getting 11. 6 plus 5 is 11. Yeah, what they said. Awesome. Any questions with that dot product? So like I said, fingers crossed that you guys would find this one kind of basic, because if you can multiply and you can add, then we can find those dot products. Now, if only we could keep it and just kind of end the lesson right here, right? Be like, all right, that's good. Let's move on to the next lesson, or that's it, right? But there's got to be a reason why we are doing the dot product, right? There's got to be more that we can do with that. So unfortunately, the rest of the lesson is going to be looking at what we can use the dot product for. All right, so the first thing actually here is I'm going to test your knowledge. It says use the dot product to find the length of the vector u. All right, how are we going to do that? What essentially are we looking for here? So when I read the problem, what exactly are we trying to find? Use the dot product to find the length of the vector u. You're looking for the magnitude. All right, I did mention magnitude when we were talking about the properties on the last page. How exactly are we going to use the dot product to help us find the magnitude? The dot product is the square of the magnitude. Okay, so there we go. Rachel's got it. If we take the dot product of itself, that equals the magnitude squared. So let's take the dot product with itself and see if we can work this backwards. So I'm just going to kind of rewrite it. What is the dot product when I do it with itself? So u dot product u. 25. All right, now remember that's your magnitude squared. So any ideas how we're going to kind of work this backwards? You got to take the square root of it, right? Because technically we want just the magnitude. We don't want the magnitude squared. So we do need to take the square root of that to get just the magnitude here. And this one's real nice because the square root of 25 is just 5. Nice job. Any questions with using that that rule, that property rule for our dot product with finding the magnitude there? Right? It wasn't so bad. All right, here's the next best thing. So we can find the angle between two vectors. And if you look in the book, they give you some diagrams. I actually have some on the next slide of what we're essentially finding. But if you have a vector like going this direction and you have a vector going this direction, the dot product can help you, well, along with some other stuff, but it's going to help you find the angle between them, right? So if these are if I can try to get my hands the best they can for the vectors there and make that angle with those other ones, it's going to help you find the direction in the middle, right? So essentially we can use the dot product as part of the process to find that distance between them. All right, so here's the formula that I'd like you to write down to find the angle between two vectors. We use cosine theta equals the dot product of your two vectors divided by the magnitude of your two vectors multiplied together. So essentially, if you're looking for just that angle, you do need to use arc cosine, or the inverse of cosine there, of the formula to find the actual angle measurement. So again, remember this top part is your dot product. It's not the multiplication of two vectors together. So I'll give you a moment to jot that down. When you have it copied, go ahead and give me a check mark or a red X, and we'll take a look at an example. Actually, I think I got two examples of finding the angle between two vectors for us. So here are the diagrams for A and B, and this is kind of what I was showing you with the hands there. You've got a vector u, a vector v. Our goal is to find the direction between them, so this theta piece. So we're going to start by finding the dot product first. So let's start with part A. What do you guys get as the dot product in part A? Tommy got an 11. We want a couple people to second that though. Isaiah's got an 11 as well. Let's see, a -4 plus 15 is an 11. All right, the next thing we're going to find is the magnitude of each vector. So let's start with the magnitude of u. What do we get for the magnitude of u? Square root of, I don't think it's going to be 15. I think it's going to be 13. Yeah. Because 4 plus 9 is our 13. Good. What about the magnitude of v? Square root of 29. Anybody want to second Tommy's result? Give her a little bit more confidence booster here this morning. Anybody else get square root of 29 for the magnitude of vector v? Yay! Woohoo! All right, well, let's see. Isaiah said square root of 21. Remember when you square a negative, it does turn into a positive. So technically we'll have 4 plus 25, which will be our 29. So just to verify that 29, that will become a positive value when we square it, the -2. I know sometimes that slips our memory from time to time there. Okay, then I'm going to go ahead and jump to that second formula. Are you putting parentheses around it, Isaiah? If you're not, make sure you do. When you square it, so like -2 needs to be inside parentheses. Otherwise, it's going to keep the negative out front and just square the 2. So when we're entering things into a graphing calculator, it's super, super picky. We need to basically put just about everything in parentheses to make sure it's doing the order of operations correctly. So check it out with parentheses again and see if it comes out correctly that time. Okay, I'm going to jump down to that second formula for theta. So we're going to use cosine inverse right away. Again, it takes a while to kind of type this accurately in the calculator, but we know we want 11, so the dot product goes in the numerator, and then the magnitudes go in the denominator. Now, as you're typing this in, you will need parentheses around the denominator because you have more than one thing happening down there. All right, so if you have more than one thing occurring in that denominator, you've got to put parentheses around it to group it together. Okay, so I'm going to type this in and show you exactly how I would plug this into my calculator. Okay, this is what I would do. I'm not sure if I have enough parentheses there to close everything off. I think I do. I probably should have put an end parentheses around my 13, but it's going to come out okay, even if I didn't there. All right, I got to make sure I'm in degree mode. I don't think I am. There we go. Yep, 55.49 degrees. And it looks like it's like an acute angle up in part A diagram there, right? So fits the bill. We'll box her up. Everybody else get 55.49 when they plugged it into their calculator? Do we need to do any problem solving on parenthesis involvement or anything for anyone? Okay. Let's do the same idea then with part B. So we're going to start with the dot product. What do we get for the dot product in part B? Yeah, they get very picky. Which is why it's so important that we need to be smarter than the calculator at times, right? All right, -5. Let me just check it. -2 plus -3 is a -5. So now we'll search on the magnitude of each vector. Start with the magnitude of u. What do we get for the magnitude of u? Careful. It should be square root 5 because we get 4 plus 1, which will be our 5. Okay. What about the magnitude of v? Square root 10. Okay. Square root 10. Again, if you're questioning how we're getting those magnitudes, remember we just take the square of each component and add it together under the square root sign. Good. All right, to find the angle, remember we do cosine inverse of the dot product divided by, parentheses here, square root of 5 times square root of 10 in that denominator. Yep, I get 135 as well. And that looks to be accurate as well for that picture in part B, right? It looks to be more than a 90-degree angle, but less than a 180. So 135 fits the bill again. All right, any questions with that piece? There's just a few more things we've got to introduce still for this lesson. All right, the next piece they talk about orthogonal. Matrices, believe it or not, are coming up in Unit 7, I think. So we are going to explore matrices, I believe, in the next unit, but I know that's probably not what you were getting at. All right, so we do have something called orthogonal vectors. Orthogonal vectors are essentially perpendicular vectors. So they're vectors that meet at a 90-degree angle, or the direction between them is 90 degrees. So instead of saying they're perpendicular, we're going to introduce a new term, and they call it orthogonal. Now, the only way that we can identify orthogonal vectors is if the dot product of them equals 0. Because if we think about it, when we go to find the angle between two vectors, we are doing cosine inverse. And if the dot product is 0 in the numerator, that essentially turns the whole fraction to 0, right? And we're looking for where cosine equals 0 on the unit circle. And where does cosine equal 0 on the unit circle? At pi, or at pi over 2, which is your 90 degrees, right? So at 90 degrees, that's where cosine equals 0 on the unit circle. So we're looking for the dot product to be 0 to know that the two vectors will be perpendicular. All right, let's go ahead, and it says prove that the vectors here are orthogonal. So if we need to prove that they are orthogonal, we're basically just showing the dot product equals 0. So how do we show that the dot product is going to be 0 for these two vectors? Yeah, actually do the dot product, right? 2 times negative 6 is negative 12. 3 times 4 is 12. So if you have to verify that or prove it, just actually perform the dot product and show that you get negative 12 plus 12 equals 0. So you actually have to show the steps and not just the end result of 0 there. So show the two numbers that you're adding together or the two numbers that you multiply together and then add. All right, not much work to that. So that's a good concept we liked. Orthogonal vectors, we can handle that because it's just the dot product being 0. I wish I could say the same thing for the last concept that we have to address in lesson 2 here. The last concept we're going to address is vector projection. So when we are projecting one vector onto another, I like to think of it almost as a shadow. So essentially what we are doing here is if you have a light source up here, this direction, like a sun, okay, and it's beaming down, and you've got two different vectors here, u and v, we are looking for the projection of u onto v. So essentially we're looking for what part of the shadow here from vector u is going to fall onto vector v. So that is what we are looking for when we hear that term projection of u onto v. So you have this vector out here. What part of that shadow is going to fall on the vector underneath it? Okay, so if you need that visual of what's going on, kind of picture the shadow of that first vector going on to the second. Here's the formula for how we find that shadow piece, the projection piece. So we're going to first essentially find the dot product between the two vectors they give us. So we do start with the dot product there. And then we divide by the magnitude of the vector underneath squared. Right, so that's the nice piece. We'll take the magnitude squared, so there should not be any square roots left in our problem, right? And then we multiply it by this entire vector that's underneath. Okay, so we got to multiply it by what it's falling onto. Let's go ahead, well, I'll give you a moment to first copy down the formula here if you still need it. So give me those green check marks when you have that copy down. And then we'll go ahead and take a look at an example. All right, there we go. So to find the projection of u onto v, and it's always a good idea to know what one we're projecting onto, right? So what's the vector that's underneath? And the one that's underneath is always that last vector v, because that's going to matter when we're using our formula, right? All right, so let's go ahead. We are not going to write them as a sum of two orthogonal vectors. We're not going to do that. We're going to just mainly focus on the vector projection. We won't write them as a sum of two vectors, so we don't have to worry about that piece. So using our formula, we do need the dot product of the two vectors to start us off. So what are we going to get for the dot products there? You get a 42. Anybody else get a 42 like Tommy? Yeah, I did too. 48, because negative 8 times negative 6 is a 48. 3 times negative 2 is negative 6, so 48 minus 6 is a 42. All right, next we need to find the magnitude of V squared. So essentially when we go to find that magnitude, you're just going to be taking the square of each component and adding it together. So what is the magnitude of V squared? Should be just 40, right? Because negative 6 squared is 36. Negative 2 squared is 4. 36 plus 4 is our 40. All right, I believe that is going to be the fraction that we use, right, to cast onto that vector V that's underneath. I do want to go ahead and reduce that fraction though. 42 over 40 can be reduced. What can we reduce that to? They're both divisible by 2 for sure. (21 over 20). Yeah, so if we can reduce, we're going to do that just for good measure, right? Now we're going to cast that onto the vector that was underneath, which was that vector V, because that's the vector that came second. That's what we're projecting onto. All right, so now we do need a calculator here because to find the resulting vector, we have to distribute the scalar to both components inside. So what is 21 over 20 times negative 6? We will get a decimal answer there, so we'll probably have to round to the nearest hundredth. And then we want to do the same thing with 21 over 20 times negative 2. So what do we get for the approximate decimals inside here? And maybe we don't have to approximate. Maybe they come out as just like to the nearest tenth and stuff. A negative 6.3 and a negative 2.1. And Tommy seconded Rachel's answer. I see Isaiah's typing. He's going to third that. Fantastic. So this is the shadow. This is how long or where the shadow is kind of ending on your vector V underneath, right? And sometimes depending on where it's coming at, the angle of the light, it can be extended past that stopping point of vector V. So it looks to be okay there. Questions with that? It depending on where it's at, it can, right? Because your shadows can be extremely long depending on the time of day, right? So you would just kind of hypothetically do your little dot 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 to extend that vector in that direction, and then you can find that projection. I did multiply the whole fraction through. Yeah, so essentially what you do there is I would do on the calculator 21 over 20 inside parentheses like that, and then multiply that by a negative 6, like so, and then hit the equal button. So you do want to go ahead and put that 21 over 20 inside parentheses. Yeah, otherwise it's not going to do it correctly, I don't believe. Okay, we're not quite done, although we sort of are. There's just one last thing I want to throw at you, and that is vectors in space. So vectors in space, now all of a sudden we're looking at three-dimensional. You have 3 components versus just 2. The good news is that nothing changes with 3 components versus 2 inside your vectors. The only thing that's going to change is maybe we're adding a third number into the mix. So if I have 2 vectors with the 3 components here, and I want to find the dot product of them. Essentially, I would start by multiplying the first components together, multiplying the second components together, and now you just got a third set that you would multiply, and then you add all of those together. Okay, and same thing like with magnitude. If you need to find the magnitude of a vector that has 3 components, you're just going to square each component, add them together, and then take the square root of it all. So really you're just adding one extra little step, and you're going to do it with the third components of your vectors. So nothing really brand new for you guys, but just adding an extra little step when you're adding or subtracting things or multiplying things with your vectors. All right, I think I have an example. I do. Let's go ahead. We'll probably finish with this slide here. Go ahead and start with A, B, and C. We'll hold off on D and E for right now, but go ahead and perform the operations in part A, part B, and part C. If you have an answer, go ahead and put it on the board. We'll kind of divide and conquer here since we're running out of time. It's always nice when our answers match up. So even if you did one that someone else already has an answer for, still put it on the board so I can see your thinking or your thought process behind it. First one looks good. You're just multiplying 3 through every component. So -6, 3, and 12. So part A looks good. Part C, we just got to remember to distribute the negative. So 1 minus -2 is a 3. -3 minus -4 is a +1, and 4 minus 5 is a -1. So part C looks good as well. I like how we skipped part B. We jumped over that. There we go. Tommy threw it up there for us. So -5, 11, 1. That looks good for part B. All right, let's go ahead and don't think that this means absolute values. What does this notation actually stand for when we're looking at vectors? Magnitude, right? So don't confuse magnitude with absolute value when we're working with our vectors. We don't do absolute value. All right, go ahead, find the magnitude of that vector in part D. Let's see what you guys are thinking there. Yeah, Tommy got square root of 40. If you want to simplify that, I believe that breaks down to something like 2 times the square root of 10. If you leave it as square root of 40, I would accept that, but we can simplify that radical if need be, because 4 times 10, square root of 4 is your 2 out front. All right, last thing is the dot product then. Can we find the dot product of the vectors in part E? Tommy got a -27. Anybody else get that? Isaias did. Good, I'm going to check it out. 5 times -6 is a -30. 3 times 2 is 6. -1 times 3 is -3. Add those all together. Results in a -27. Very good. Any questions with those vectors that have 3 components versus the 2 that we've seen in the past? So really nothing spectacular or extra. You just got to extend the process a little bit when you're finding those. Okay, that's all we really have time for, which is okay because we were just going to find the dot product of a few things and then the angle between them. Again, this is your, if you were to see a problem like this last one, actually go ahead and see what this results to so you can get the vectors there, right? So 2 times cosine of pi over 4. What is cosine of pi over 4? So using your unit circle, what value is pi over 4 or cosine of pi over 4? Yeah, that's your square root 2 over 2. So if you were to be presented with a problem like this, that's technically looking at the square root of 2. And sine of pi over 4 is the same thing, right? That's your square root 2 over 2 again. And then moving on to the second vector, what is cosine of 3 pi over 2? So that's on the y-axis between quadrants 3 and 4. So what's the cosine value there? 0. And then what is the sine value at that spot? Yeah, so I would transform those into vectors and then proceed forward with finding the angle between them. Okay. Any questions with that one? So as soon as we turn those into vectors, hopefully the process becomes a little bit more clear. All right, you guys are good to go then for lesson 6.02. Give it a go. I think 6.01 needs to be handed in for sure this week, and I'm guessing that 6.02 might extend into next week, Monday. I'm not positive. Okay, that's what I thought. You should be able to complete 6.02 this week, though, if you wanted to. I think it's due probably Monday of next week, so if you don't get it in, you do have until Monday to do so, but make sure you get 6.01 turned in for this week for sure. Next week, we're going to go ahead and we're going to look at 6.03 in Tuesday's class, and then I have kind of a review activity for us for Thursday's class, because we've learned a lot of information on vectors in the first 3 lessons, so we'll review next week, Thursday. All right, that's all I got for you guys. Have a great rest of your week. Have a great weekend, and I'll see you all Tuesday morning again. Bye, everyone.
Recording stopped.